ॐ सहनाववतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Yeah, we were looking at yesterday the total Lagrangian formulation. We just took a look at the first few steps which we had done before we continue with this. What we said is that we define a functional. Functional is now in terms of strain energy. We said that psi will replace it by W, which is common in most of the papers. So this is the strain energy term. This is the work done by the external forces or the potential loss due to external loads. So where you know that phi external consists of two terms. One is the internal force term and the other is the external force term, where T is the traction vector that is acting on the surface. And so we take the first variation of this delta phi. The first variation of delta phi, first variation which is delta phi, is given by dou W by dou Cij into d delta Cij d omega. That's for this because we had written W in terms of Cij. And the second variation of variation of the second term is given by rho 0 dou ui and so delta ui ti and so on. Yes. So this is where we stop, and we of course know that Sij can be written as 2 into dou w by dou Cij. Okay. Now let us now take this term. So this means that I can do a small substitution. What is the substitution I can make? I can just remove this and I can substitute this into that expression so that I can write that as dou Cij into half of it. The 2 is there, so that has to come here. Yes, Ij. Right. Now let us see what these terms are. Ultimately I have to write the whole thing in a form, a variational form, such that it will we can derive the equilibrium equation that is incidental. We know that, we have done this before. And next is to make the way clear for implementation of the finite element formulation. Now, of course, all of you know that dou Fi I can be written as, how do you write this? This is equal to dou of this, we had seen this before, xi. This comes from the fact that ui can be written as xi minus capital Xi. Okay, so delta ui and dou xi, from here you will get that dou of del ui is equal to, note that if you don't remember, this is equal to dou xi by dou capital Xi. Yeah, these are the things which we saw in the last class. Now, let us now try to replace this del Cij or dou Cij. What is Cij? We had seen this before. Is equal to half. What is C? Half. Or sorry, C is F transpose F, and that's what we substitute in E to get half F transpose F minus I. So this is equal to, so C is equal to F transpose F. Right, this is in terms of the tensor notation. So suppose I want Ij, what is that I get? Actually, if I can say from here delta C is equal to F transpose F plus F transpose delta F. So write that in terms of, let's see, integral notation here. How do you write that? Note that Fij is a, so here you have to write in terms of integral notation. How will you write that term? Delta F transpose F. How do you write this in integral notation? F transpose F, how do you write this? How? So delta F transpose F can be written as delta F. So will it be IK Kj or say I say for example F I J, right? Okay, this is what is F transpose F, right? Plus F, again same way I write it, I J, right? Now substituting this into my previous expression, okay, and invoking the, I'm just going to skip a few steps and invoking the Green's theorem, I can write down this expression here. Okay, look at this expression. I can write down this expression as, and by the way, what do we mean by invoking Green's theorem, or the integration by parts in say 2 and 3 dimensions? Let me write down that. That's quite simple. Suppose I have omega, I have some quantity dV is equal to uv minus integral v du. So this will be phi ny ds minus integral v du. That means that dou phi by dou y psi right. So invoking that, I can write down this expression here. Okay, let's see how you write this down. Substitute for delta C ij, okay, and then you have these terms here. Write that down, and what is that you will get? Look at these terms. Look at this term. Look at this term. Look at this. Let us see. In fact, the first step is that delta C ij. So you can combine this. You can say that delta C ij, okay, can be written as delta F I F J J S I J, if I want to include. You can verify this, okay, that you can write down delta C I J S I J as delta F I F J J S I J, because F transpose F is, what is F transpose F? F transpose F is symmetric term. Sij is symmetric. You can verify that. You can write down this fashion. Now, let me substitute this into my expression in delta phi, so that the delta phi expression can be written as, I'm doing it for you. So delta phi expression can be written as, what is the first term? Integral half of I f j j s I j minus delta phi external terms. Okay, now I think just a second. This is half because that's symmetry, so it should be half here. Half of that will be, sorry, this has to be half here, so that half will go off. Because of the symmetry conditions, you will get only one term. It's quite straightforward. You can verify that. So, in other words, you multiply this term here into Sij, you will get what I have written there. Okay? Just multiply that. So now, let me invoke my integration by parts in 3 dimensions with respect to that. One of the things I do is, before I do that, is to substitute what I know as dou of dou ui, dou xi, this place, as delta of ui, comma, what is that I should get? I, right? What I have done is essentially delta f I, I have substituted it from this expression here into that expression. So I have written this as delta ui comma I f j j s I j minus delta phi external terms. Now let me now at this stage invoke my integration by parts theorem, so that this term, quite simple, but only thing is it involves, you have to be very careful with the notations, indical notations, that's all. There is nothing more than that, very simple terms. So that's the left hand side. So that will consist of 2 terms. So the first term is, sorry, we have to put dv, and of course all these integrations are with respect to the reference configuration. So is equal to, first term is surface term, so this gamma term. So what is that we have written here? So what do we get from this? How do you write that? We can, okay, I'll give you a clue. We can treat the phi, okay, to be what in this case? That is our phi. If you have a doubt, this can be treated as our phi, and this delta u or delta ui can be treated as psi, right? Now apply the theorem. So what will you get there? So you will get delta ui, phi will be there, f j j s capital I capital J, and then instead of that ny there, you will get ni term, right, at this place instead of ny here. If you need time, I would just wait for a minute. You can write it down so that there's no confusion. Okay? So let me repeat just what we did so that there's no confusion. What essentially we did was to write down the potential energy, okay, then in terms of C and S, okay, then what we are trying to find out is the variation of C, that is delta C, from the fact that C is equal to F transpose F, and you can write down delta C ij. Okay, after this multiply by Sij, we find that because it's symmetric, you can do a small jugglery and find that half of delta C ij Sij is equal to this quantity. Okay, what we are going to do is to substitute this back into our potential energy expression, right? That's what we are doing. So that's the first step. After this, integration by parts, that's the next step that we are doing. So in integration by parts, I find that the first term for this can be written like this, and I have identified the delta ui to be phi, fjj sij psi, and fjj sij to be phi, so that the second term here minus integral up to omega 0. Okay, how do I write now? Delta ui, very good. Then the second term fjj, that's the second term, f capital J, then s ij, the whole thing, okay, comma, shifting this I, right, comma I d v. Is that clear? Yeah, psi and phi, this is psi, this is phi. So the first term consists of phi psi n, that's the first term. The second term consists of, since psi has a derivative, we are shifting the derivative. So psi, dou phi by dou y is what we had in the formula. So now this y is now this capital I. So you will get dou phi by dou xi, that's what you will get. So which means that this whole thing is derivative of I. Is that clear? I'll give you a minute, just see it. If there's any questions, I'll answer it. Pardon? Ni. Yeah, Ni term will come here. The second term here. Here it will not come, obviously. Look at this. Please look at this formula again. Please look at this again. You will see that this is our psi and phi. Psi comma I, phi dv psi. So these are the two terms. First you have ny. You don't have an ny term here, right? So this is exactly what we did here as well. Yeah, normal. Yeah, normal in the reference configuration. Nx, ny, and indicid. So that is the ni term. Of course, all of you know that the summation is valid here. Okay, we have assumed that the summation, whenever I write, that's automatic. I need not even tell you. Now, this is my first term in my delta phi. So substituting it into my delta phi expression, okay, it consists of two terms. So how do I write delta phi? Is equal to, there are two terms there in the delta phi external. One term is due to the what? Internal, what we call as the body forces. So both of them would come under the complete integration, so that you would write that as delta ui into f jj sij comma I dv, or let me put the dv a little later. Then what's the second term? Minus get back to the first one, delta ui rho 0 bi. So minus rho 0 bi dv or d omega plus the second term here delta ui into fjj sij ni plus or rather minus ti term ds, okay, that's equal to 0. Yeah? Yeah. fjj, okay. So, that's correct. So, which gives us the equilibrium equation. The first part is the equilibrium equation that you get, and the second, whatever is inside the bracket, both of them are equal to 0. This is equal to 0 and that's equal to 0. So, that gives us the, since delta ui is a variation that you are going to impose, delta u small I can be assumed to be delta u capital I. So, this is going to be our equilibrium equation and this is going to be our traction boundary condition. Okay, this is exactly what we would have got in the case of the small strain as well. The approach that we have followed here is exactly the same as that of the small strain case. Yeah, I'll write down the equilibrium conditions now, separately if you want. Let's get that. What is inside the bracket, the first one, is the equilibrium equation for the reference configuration, which can be written as one second. I think it should be ij. Please note this thing. We had, I think we wrote that in the previous one. This is the problem. There's so much of i's and j's that you have to be very careful. Please note this. This is I. This is I. This is I. Okay. So that the first equilibrium equation can be written as I j s I j comma I plus rho 0 bi equal to 0. Now it's usually that since this had a delta ui term, okay, here, it's usually there is a small, I would say, jugglery that is done. Instead of making delta ui the same as delta ui, you would usually say that this term has I. Okay, so that both of them are the same. I want to show, so that this would actually have plus delta I be rho 0 pi equal to 0. And the second term is the second term what you have here is the surface traction term, and that is written as fj j s ij. The same way, put a delta I t bar, is that I? Yeah, I is equal to 0. So this is the surface traction term and this is the equilibrium equation term. Check, I hope I have all the indical notations are correct. Yeah, obviously, because delta ui, both of them should be the same, so that's why we had delta u capital I, delta u small I we had. So the connection is that it should be delta I. Delta I should be equal to I. Okay, that is why we had put this. When both of them are the same, then this term will exist. Because you remember that delta U capital I was the one with which we multiplied the second one, because all of them are summations. Okay, hence we had put that. You can sum that up and you will see that that exists. Okay, so I know it's very tedious, too many indical notations, but nevertheless the concepts are very simple, and having crossed a major hurdle, now things are much more easier to work out once we go into the finite element form.
So that will be Fij or Fjj?
Fij.
The second one.
Sij.
No, below that.
Traction, look at that.
That will also be I. Fij. That will be I.
Fij, correct. Then there also, where is the, yeah. So that means here also Fij, right? Yes. Fij, Sij. See, when you just logically follow, it would be very simple. Fij, correct? Sij as delta I, Ti. I hope there is no other. Yeah. Sorry, here also, because that will be the term, right? Down also. Right. I'll just give you 1 minute. Just look at this. I hope my I's and J's are right now. Okay, just look at this and that. Everything is fine. Now, though we have derived this, this is not of much importance for us, because we will go back to the first step. Okay, remember that the first step is the potential energy theorem, and the second step, where we said delta phi is equal to 0 term. Okay, delta phi is equal to 0 is actually our virtual work type of principle. So we will start from there, and the procedure is exactly the same as we did before. But only thing is that our B matrix, there are additional terms like F's, and hence our B matrix would all be different. So as a first step, let me write down for isoparametric formulation, Xi is equal to sigma of, I'll just explain what this alpha is, into Xi alpha, where alpha is equal to 1 to number of nodes per element. This is our regular, where of course this n is the shape function written in terms of, if it's 2D psi eta or psi eta tau if it is 3D. And alpha is equal to 1 to any n, so if it is an 8-dotted element, then this will be 1 to 8. Now it's going to be quite cumbersome to write these expressions now, so you have to, I'm going to write only in a slightly different form than what we had written before. Okay, so that is my first expression for finite element. Just please watch the indical notation. I hope I don't make any mistake on that indical notation. The second one is, say, UII. How do I write that down? UII, because UI will also be again written in terms of the same thing. So let me write down that. Say UI is equal to sigma alpha is equal to 1 to n alpha UI alpha, where this UI alpha are the nodal displacements, from which now I can write down Ui comma I, this is what I want because delta Ui is what I want. Ui comma I is equal to sigma n alpha I comma I U I alpha. I think alpha was here, or where did I put alpha? Yeah. alpha comma I, sorry, we'll put that as I, not I, alpha comma I, ui alpha, alpha is 1 to any. Yeah, so that is u I comma I, right? So if I want to write this as delta ui comma I, that will be 1 to any n alpha I delta ui alpha. And suppose I want to write down delta E. How do I write down delta E? Say for example delta E I j is equal to half of delta U dou of delta U I dou. This consists of two terms. Where how do I get this? This I get from E is equal to half of F transpose F. Okay, so minus I. So delta E I j is equal to the same thing what we did for C F transpose F. So delta U I delta X I F I j. I hope I'm correct. Yeah, that's the first term, F transpose F. The second term plus the second term will be, so this is F transpose F. Okay, so dou of F transpose, that becomes this F plus F transpose. So F transpose, how do I write? F. So J. No. I right into dou of delta U I j. Just check the integral notation. Is that right? F I dou of delta U I dou x j, right? So this will be delta E I j. Now the reason why we write delta E I j is because ultimately we are interested to write down in finite element formulations in terms of strains, green strains. That's the reason why we have written this down in terms of delta E I j. So in other words, that delta E I j can now be written as in simple terms as delta E I j. I have reason to write it like this: half of delta U I F I j, right? It's going to be huge expressions, plus F I delta U I comma j. Right? This is the delta E I j expression. It's very useful to write this in slightly different form, in the matrix form, because that's how we are going to work. So delta E 1 would be, of course, there is summation in terms of I. So in terms of in 1 can be written as delta U I comma 1 F I 1, right? Look at that. So in other words, delta E 1 is 1 and 1 I substitute, summation about I, right? So if I want to write down 2, then it is delta U I comma 2 F I 2, delta U I comma 3 F I 3. So if I want to write down in terms of the I mean F1, suppose I want to write down 1, 2. How do I write this down? Half of delta 1, 2. Yeah. Delta u I comma 1 plus sorry f I comma 2 plus second term. Second term here. F I1 delta u I comma 2, where summation of I is intended. That is, in other words, this whole thing consists of 3 terms here, 3 terms here, huge terms. Delta u 1 comma 1 f 1 comma 1 comma 2 plus delta u 2 comma 1 f 2 comma 2 plus delta u 3 comma 1 f 3 comma 2 plus f 1 1 1 delta u 1 comma 2 delta f 2 1 delta u 2 comma 2 f 3 1 delta u 3 comma 2. So those are the terms that are involved, right? It's a huge terms. Delta
the second term of first
I comma 2. Oh, sorry, not. Yeah. I2, there's no comma, sorry. I'm sorry, Fi2. Now, it's usual practice to write this in terms of 2 gamma. If you remember, that's what we had written down. It's not in this delta E epsilon terms were not written as in terms of epsilons, but in terms of gammas. So this half is usually taken out, and that is how you write delta E. This is what we did in the first course as well. So you can continue and fill this up. Right? Please fill the rest of it. Now we have another huge expressions coming up, because unfortunately we have to now substitute what all we have here. Okay, what all we have here, we have to substitute it into this expression. Okay, then let us see how delta E would become. Okay, let's see, please try to substitute it. Okay, this is just an exercise in algebra. So let's say just substitute the discretized quantities here into this expression. So first term, I'll only write the 2 terms, then you have to fill this up.
where do we compensate for?
Yeah. So let's just write this down. First, only the first term, delta u 1 1 1 comma 1 f 1 1 plus delta u 2 comma 1 f 2 1 plus delta u 3 comma 1 f 3 1. Right? That's the first term. We have it like that. I'll just remove all this. We're just looking at only the first term. So I'm going to substitute now delta u 1 comma 1 from my discretized quantity. I have, remember, u I comma I in terms of n alpha and so on. So what will happen to that? So this will be sigma n alpha Yeah, comma 1, then the second term will be u1 alpha. Since delta is involved, there will be delta u1 alpha sigma of this multiplied by f11 plus sigma n delta u2. What will I have? Alpha comma 2 comma 2. Okay, so delta alpha two, no, 1, 1, yeah, into u delta u 2, right, alpha into f21 and so on. It will be a huge expression again. So now I am going to divide this into two categories. In other words, sigma of n alpha is divided into n alpha will become b alpha. Okay, so that let me write down the first one like this. This expression can go on. You can verify that. So the first term. So what I am going to do is I am going to write that down as in terms of, note this, in terms of alpha. So that this will be in terms of delta 1 alpha, delta u2 alpha, delta u3 alpha. So that will be f11 n alpha comma 1, okay, then f21 n alpha comma 1 and f31 n alpha comma 1 multiplied by this. This will be the first term of this sigma terms. Okay, so this is what I'm going to call this as B alpha. This will be a huge matrix again. So you can work with this is the first term. You understand? So this will actually be this will go on. So this will be B alpha term. Okay, there will be another for alpha is equal to 1. This will be like this. So there will be another B for alpha is equal to 2, another B alpha is equal to 3. Okay, so complete this. I am not going to write this down. Maybe second term we can write down. So f12 n alpha comma 2, f22 n alpha comma 2 and f32 n alpha comma 2. That will be the second term. That will be multiplied by this. So in other words, so you can please fill this up. And in other words, delta E can be written as B alpha delta U alpha. This is just indicate that they are nodal quantities. Okay, where summation of alpha is intended. So there will be, say if there are 8 nodes, there will be 8 B's like this. For each of the node, you will have delta U, say we are talking about 4th node. So in other words, this will be written as there will be a B1, okay, indicate having instead of where alpha is equal to 1 in all these places, B1 into delta U1, okay. This one indicates this is a vector. So in other words, this will become 1, 2, 1, 3, 1. This will be the 3 entries for the 3 degrees of freedom of node 1. Like that you will have, look at that. This is the problem with the total Lagrangian. Huge matrices you are going to get, and programming all this very carefully, even when we write I and j, you have to be careful. So this again, delta u1, 2, delta u2, 2, delta u2, 3, and so on. You will keep getting this for yeah, 1, 2, 3 are the degrees of freedom for node 1 in the 3 directions.
It will be delta U1, down will be 2.
Okay, yeah, because alpha I had written it like this. If you want alpha, keep it at the top. So if you want, you write it like this. This is what you're saying. So because alpha is here, I put it here, so you can write it like that. So 2, yeah, this is right, 2, 2, 3. Like that, you will keep adding B alpha terms. So there will be this will be a big, chunk. But instead of writing all this, instead of writing all these things, we will stick to just B alpha delta U alpha term. In fact, this B alpha can be viewed as, which I'm not going to do again because they involve huge matrices. I refer to Zinkiewicz, okay, volume 2. All these expressions are available. Okay, maybe tomorrow I'll just summarize and write down all the expressions in one shot, because deriving this is again going to take a lot of time. Actually, you can see that this can be split up into 2 terms, a linear B alpha term and a nonlinear term. So this BNL, very famous term, BNL is the addition to BL. BL is what? Our old B matrix, is actually the one which converts delta epsilon ij, which we had seen, to delta E ij. Okay, so this is what we are going to use. Now we will continue in the next class. I will summarize all the matrices that are there and then finish this expression. I am not again going to come back to total Lagrangian. We are not going to derive it in so detailed fashion, but we will finish this derivation putting all the matrices in place, just to give you a flavor, a feel of how terms are involved in the total Lagrangian formulation for nonlinear finite elements. We'll stop here and continue in the next class.